Thank you very much, Steve, for kind introduction. I take this opportunity to thank AIST for giving us this opportunity for presenting our paper. This paper is written by me and along with my colleague, Mr. Naveen Singh. Both of us are working in Jaiswal NICO, and our co-author from NIT Raipur, Mr. Manoj Chopkar and Mr. Sanjeev Das. They help us in doing this metallurgical test and for clarifying the theory, and we believe in practical. So in a combination we work together. By changing the right from the iron steel making stage up to the rolling mill, we would like to have different changes in that so that to first achieve the properties. As you all know, the high carbon is used for different purposes. Bridge cables and tire reinforcements are the very critical one, and for this we have worked, and what we tried to achieve it by controlling the chemistry during the steel making and during the hot rolling of billets into wire rods. As we all know that we have to achieve the cold drawability, and that can be done by faster cooling so as to avoid any grain boundary cementite precipitation in the wire rod post hot rolling. Yeah, so typical chemistry is high carbon. This is 0.8%. This is a typically eutectride steel, and here what we have done, the steel making process up to this billet caster, reheating the furnace, and in the rolling mill. What we have done, yeah. So as we go through rolling mill, there is a roughing mill, intermediate mill, finishing mill, wire rod block, laying head, and then cooling conveyor where we have got blowers and the hoods. Then later on, one more thing is there. You just please press it. There is a coil forming. Yeah. So this is the process of making high carbon wire rods. Next slide, please. Now our process is for what we have done pre-rolling stage, and then what we have done after rolling. So in the pre-rolling blast furnace, what we have done, we have restricted the titanium ore feed so as to minimize inclusion of titanium in the steel. Next, when we come to the steel melting shop, we try to control the superheat, casting speed of the caster, and EMS steering with so as to achieve a very good structure without any center line segregation. When we come to rolling mill, reheating furnace prior to rolling, we control the retention time from 2 hours 15 minutes to 2 hours 45 minutes, and we maintain the temperature of soaking zone around 1170 degree. This helps in controlling the decarb as well as the homogeneity of the structure before rolling. So as we have seen how we control the titanium method, we have seen total 10 batches of steel melting cast we have checked, where we have found in the one highlighted in the pink color, there are total 5 area total. Out of that, where we have seen where we have not used titanium in the iron ore, and we found the results were better. The titanium was less than 4 micron in almost 55 samples where we have not used the titanium ore. Coming to steel melting shop, to avoid the center line segregation, what we have done, high current and low frequency on the left side of the figure 1A, you can see the structure is very clear, and when we use high current and high frequency 6 Hz, that time we found there is a central line, some problem was there. This is more a shrinkage type of things. Now, reheating furnace, This is a reheating furnace, walking hearth type. We made different data with the retention of the furnace. This was 160 input we have used for making the 12 mm wire rod. As you can see, where the retentions are high, 2 hours 45 minutes or 3 to 3 hours in the point number 3 and 7, the decarb level was high. It was more than 1%, and remaining all where the retention was less, we found that decarb is less. Now coming to the rolling side. In this, what we have done, initially we made this experiment with 5.5 and different combination of mill speed along with conveyor speed we have tried. As you can see on the top, low density factor, in 5.5 we could achieve 0.15 and less, and when we achieved that figure, the cooling was very good and the properties of the material was very fine. When in 12 mm rolling, we played with the speed and the conveyor speed, and different loading density factor we have seen. So the old practice was to have load density of 0.1, which we reduced to 0.06 to 0.07. Again, there was some changes made on the laying at temperature, 800 to 890, and the new practice 890 to 900. Conveyor speed, different combination we tried, 0.6 to 0.8, and the new speed was 0.8 to 0.9. And one thing we have tried is because it is in Asian countries, what we find here, the temperature is a bit high. So whatever these blowers are setting this air, the temperature is high. So what we tried here, we have put some water pads, and this has helped in increasing the cooling rate from 11 to 12 degrees to 14 to 50 degrees. There was an increase of 2 to 3 degrees centigrade per second. Now this table shows the trial results of the different parameters. Mill speed we have played between 18 to 20 meter. In the new practice, we have gone from 15 to 17 meter. Laying at temperature, from 2 to 3 experiments we have done. I am just putting 1 or 2 in this. Conveyor speed we have varied from 0.6 to 0.8, and then for the new practice we have gone a bit higher. So as you can see, the load density factor has changed when we have gone for lower mill speed and higher conveyor speed, and the rate of cooling was achieved higher with the help of this cooling pad. Now we can see the microstructure. When the speed was less and the load density was higher, we can see significant carbide network on the left side, which A and B. When we have gone for higher speed, lower speed and higher conveyor velocity, we could see the comparatively less carbide network. Similarly, the coarse perlite and a laminar structure, which is not desirable, when we have gone for the modern practice, we could see the fine perlite and close laminar spacing. This is the requirement of grain boundary carbide from the different customers. The idea is to have type A, practically very clean structure. Okay, to some extent type B is also permitted, and C, D is not desirable because it will lead to the breakage of the high carbon material. Yeah, these are the trials of the GBC. As you can see on the left side with the old practice, type A, the number was less. You can see only 20% out of the 36 samples we have seen. Type B was more, and when we have gone for the changes in the parameter, A type GBC acceptance was much better, and A and B type, when we put together, it was almost 85%. When we see the tensile strength, there is an increase in tensile strength from 1120 so almost 1140, and RA was also better. It has improved to more than 35%. Yeah. Now coming to the conclusion part. As we have all seen, when titanium nitride inclusion, to avoid that, we have not used titanium ore in the blast furnace. Normally, what we tell, we inform blast furnace, they take 6 hours before the steel melting is done. We stop feeding the titanium ore and we got the results in a better results. EMS parameter having high current and low frequency, it gets very better result to control the central line segregation. Decarb was controlled by optimizing the retention time and temperature in the reheating furnace. Optimum combination of mill speed, conveyor speed, laying head and the cooling condition. It has helped in controlling the GBC, resolve per light, and giving the good mechanical properties. Introduction of cooling pad at the cooling conveyor has helped us in increasing the higher rate of cooling so as to have a good metallurgical structure. You must have seen the previous slide. We have got in 12 mm rolling some B and C also. So this is mainly because of insufficient cooling. So now our next trial is for high speed blowers so as to get the enhanced cooling rate and to control the resolve per light and restoration of GPC to avoid the GPC. This is all about me. Sorry for the interruption in the presentation.
Speaker on.
You can contact us for any of the things. Our email address are there. Now we are ready for any questions you would like to have.
Speaker on.
Yeah, what we have done after rolling up the block, we have got water boxes. So that helps us in controlling the laying head temperature. And once the laying is over, say 880 to 900 degree, there are blowers, and since the blowers were not sufficient for this PSC 116 mm cooling, we have added some water pads. So what is happening, it is reducing the temperature of the ambient air. What is happening, these pads, what we are doing, we are putting some water on the top of that. So this is a typical thing you can see in any of the Asian countries where the temperature is very high and people try to do it. This is one step we have taken, and then what we are planning now, we will go for cooling tower so that we put spray water on that cooling pad, and so it helps in reducing the temperature. It is only a sprinkle of water. On the pads there is sprinkle of water.
Air is passing.
So and the air is passing through that.